All right, so as far as the PowerPoints go, it seems like there's a lot, right? But you'll notice that I have boxes. Here, let me show you an example. So I have boxes. Do you see these boxes? Right? How you get them go away is you watch it in slideshow mode and you click, right? They're animated and they go away. But I had a student one semester and I decided to leave them up too, even having explained that. And I probably need to write a note somewhere here or even on the PowerPoint slide. These PowerPoints are repeated ones. All these are ones, PowerPoints with boxes revealed. So when you click on them, right, the boxes are not there, or they're see-through, I should say. So see, I made it, right, where you could see through them. Because they couldn't figure out how to get the boxes to go away. But there's a reason why I did that. And, you know, as it relates to the bonus, too, is that when you write this stuff out, right, as you're reading and stuff, and as one of your classmates pointed out, if I go through the effort to do something like that, do you think the stuff inside those boxes is important? Yes, definitely. Definitely important. So, because, too, right, time is of the essence, although I love to do the polls in class, right, we're running out of time. So I turned on the first one that would normally be a poll, and I even put the date for before class. And hopefully we're going to get through 2 and 3 today, and I'll turn that one on. And I really need, right, really need for you guys to do these before class, because then, you know, the important thing is that you're studying and you come to class and you ask me questions if you don't get why you are getting certain things wrong, right? Okay? So that one's turned on, and I'll turn on the next one. I rescued something. Thank you for being, when I first started teaching, the internet wasn't as accessible as it is now, which worked in my favor because I found on one of my old drives, these were some web pages that the Nobel Prize website had up, and they had a game that went around with it, and it disappeared. This semester, my online students who were ahead of you this semester were like, hey, we can't do this assignment, the links are broken. And some of you guys noticed too, because I had the links on a previous page, which I don't remember if I deleted or not, are gone. So for this assignment, notice too, I'll quickly go to my student mode. That's okay. So I renamed it too, which helps. Immunology reading. So this is a PDF, thankfully, of the 2 web pages that they originally posted, because I actually printed this at one time for my students. So notice the date, 2010. 8 years later. Thank you for saving it, Erica. I can't link to this, right? So their official website no longer hosts this page or the game anymore, which really sucks. But you can see, like, they got cute little pictures, but I usually have you guys read this before we even start immunology, because it is a really good summary. It's got cute pictures. It's written in a language that's very understandable, right? And it's probably one, I usually reread it every semester. I haven't yet, but probably before Thursday I'll read it again. So they had one page that was an overview, which is a really great overview, right? And I mean, the pictures are great, because they're somewhat comical, and but they really help you get it. And then they go into a little bit more detail even, which really helps out with this class, right? And they've got cute little drawings for the cells we're going to talk about, right? And some of the processes that we're going to talk about. And this is a really great schematic as well. similar to like kind of what I drew out on the board, right, for that bonus assignment. And so I want to reiterate that, and I'll check that too because and make sure it's in the right spot in my grades. But I'm going to do that later because I'm going to check for my other class. This one where you're watching the videos, and do this as soon as possible, even though it's, but you can always watch them again. This right here is worth 10 points if you do it all. And it's videos of me drawing on the board, low tech way back when. And I really wish, especially having this room, we could redo this, but again, we always get time taken away from us, storms and whatnot. I remember those of you guys that had kid problems on Thursday, I took attendance and then I erased it and put it in my Excel file because I'm required to take attendance and turn it into the department. But I erased the attendance so that it doesn't count against anybody who wasn't here on Thursday, right? We even got an email from our vice chancellor that said, don't count it against your students for being absent. But I have a kid too, so I understand, and I usually don't need to be told to be generous because I already understand that it sucks when things like that happen. So, what else did I want to go over? So we'll have one more discussion board, and yes, I haven't graded the other one yet, but I will soon to get caught up on my grading. But I want you guys to do this assignment first. And I'll give you till next week to do it, but do it as soon as you can. It really is worth your time. And as you can see, it's not a lot of pages, right? And I literally just want 2 comments so that I know you read it, okay? You don't have to write me some big long notes, right? Because y'all, I'm just really going to scan it real quick to see what you wrote and give you your 2 points, okay? But it's really worth your time to read that. So, speaking of time, let's go to Innate Part 2. And this is on inflammation, right? So they say this is a physiological response. Some people argue whether it's an immunological response or not. You had a question, Dylan? Oh, okay. All right. Still confusing you, yes. Okay. So and then last time beforehand too, I even wanted you to watch some videos. So what starts this response that we call inflammation, right? There are mediators, and one of them you've heard a lot is histamine, right? Because for some of us, we respond to things that we don't need to respond to. These are called allergens, right? And so a lot of us take what's called antihistamines to stop this inflammatory response against things that we don't necessarily need to be inflaming, right? Cytokines is the general name for these chemical mediators that the immune system works on. So your endocrine system, right? What are the chemical mediators of the endocrine system? Anyone know? Hormones, right? And if you've studied endocrine, right, in AMP2, you're like, oh my God, right? Oh no, cytokines are 8,000 times worse. And we still don't even know everything they do and how they do it. But, these are like the hormones of the immune system, right? So these are the chemical messages that the immune system uses to communicate what's going on, okay? And so we'll talk about a few of them. The good news for you guys, again, not graduate level immunology class. We're not going to memorize but one of them, right? But have a general idea of the different names of them. And so we'll go over those. And so why inflammation? So most of the time we're trying to stop it, like I said, like when it's happening because we're responding to an allergen, something we don't need to have inflammation against, something that's not going to hurt us. Pollen is not going to grow in your body, right? But for some of us, our body responds to it with inflammation and an aggressive immune response. This is why they're called hypersensitivities, right? You're overly sensitive. But the main purpose is when you have damage, right? when you have a cut, when you have a wound, is to contain that site of damage. We want to keep that response local too, right? We want to just attack the things that got in that local area, and we don't want to let them out. And of course, if something got in, if an invader got in, a bacteria got in, a virus got in, we want to eliminate that invader. And then of course, if damage happened, we want to restore function to that tissue that got damaged. So we've all experienced inflammation, right? What do you see or feel, right, when you have inflammation? How do you know you have inflammation? Swelling, heat, redness, it hurts, yep, it's painful, right? And depending on where it happens, you might even have loss of function. So they call these the 4 cardinal signs, right? Swelling, redness, heat, pain, right? And then sometimes loss of function. Okay. If you're a clinician, right, there are 2 words that unfortunately are used inappropriately a lot, and their strict definition are not used appropriately. Signs are things that you can actually see and measure. So can you see and measure swelling?
Sometimes.
Sometimes, yes, right? Significant swelling, yes. Redness, yep. Heat. You can't measure heat? What's a good old thermometer for? Right? You can touch it and even feel that it's hot, right? Can you measure pain? No, right? I'm sure they're trying to figure out a way to do this, right? Like stick electrodes on you and actually but pain is one of those things that is what's called actually a symptom. Symptoms are things we cannot measure, right? So veterinarians, right, only deal with signs, things they can measure, which is somewhat good, right? There's no such thing as Dr. Dolittle. There really is no one who can talk to animals, right? You can assume, but I'll tell you, there was a horse we called Hocus Pocus. That was his nickname. The veterinarian came and numbed his entire leg. He was still limping, right? Veterinarian goes, I don't know what to do. Yeah, I don't know what's wrong with him. I don't know why he's limping. I've checked everything out. There's nothing structurally wrong. I've numbed the entire leg. He shouldn't be feeling anything. He's still limping. We put him out in the rest paddock. Literally, the veterinarian is driving away. Hocus Pocus is running laps, not limping anymore, in the rest paddock. Right? Explain that. We had him in the beginner riding classes, and he was tired of the beginners that don't know how to ride, and he was tired of getting his sides banged on. So he faked an injury. I kid you not, he frickin' faked an injury. Dogs will do this, right? They pick up their paw. Oh, right? They want to treat, right? They learn these behaviors, right? So animals are tricky. People are tricky too, right? Because they'll say they're in pain to get pain meds when they're not in pain because they're addicted to them, right? Symptoms are a tough thing to deal with, right? Because you have to rely on the patient's information as it applies to symptoms. We're not going to get real picky in this class, right? We're still going to call these, all 4 of them, signs, even though pain is actually a symptom, right? Unfortunately, symptoms and signs are used interchangeably, but now you know the difference, right? Okay, so I wasn't going to spend the time, but I'm going to show one of these videos because I really think it's worth our time. So as we watch these, right, these are important questions that we need to know the answers to, right? What caused the release of the inflammatory mediators? And of course, are we going to go over these? Yes, it's the next couple of slides with boxes to reveal. How do the white blood cells get to the damaged area? How do the white blood cells get out of the blood vessels? That one's a clue. And what do the white blood cells actually do, right? And they're actually called white blood cells because if you draw blood and spin it down, you'll get all these red blood cells and you'll get this white layer in the tube. And that's where all the white blood cells are because they're not quite as heavy as good old red blood cells. So In presentation mode, you see I already clicked on this one, my favorite one. So I already got it pulled up, ready to rock and roll. And we can skip any ads. Haha. And go right to it. Let's see. Except I'm not sure about volume, so that's one thing I forgot to check. Darn it. Pause. I have to hit the right pause too. Someone might have muted volume on this. No. Oh, bummer. I always forget something, don't I? Important. Because it's not playing on y'all's end, huh? PC, volume. Oh, bummer. Alright, that's okay, because I'll talk through it. It's still worth it. Alright, so. The other video I like because it starts with a splinter. This one calls them leukocytes. So this is a site of damage, right? So these cells are screaming. How do they scream? Look, these are their chemical mediators. They're called cytokines. They're releasing these. They bind to the endothelial cells, right? This is a blood vessel. Those endothelial cells change. Oh, I forget this is a damn touch screen. Don't touch it, Erica. And you see proteins, receptors, and on our white blood cells, they have receptors. And so the white blood cells literally start rolling along, right? Because they're interacting with these receptors. Till they get to a point where they literally stop and they squeeze in between. That's called diapetesis, means oozing, right? So they're oozing into the area. So they're heading to the area where there's damage. So if there's invading microbes, they're going to infect. And this is why this one's my favorite video, because look, y'all, this is in a mouse, right? Probably ultrasound. You literally can see as they're interacting, they're rolling, the white blood cells, until they actually start going into the tissue. And so you can see, they're going to point to them in a second. I've only watched this video a million times. They're talking about some other stuff right now. They're talking about that this is a vein, right? And up at the top is an artery. For those of you guys in A&P, we'll talk about why this only happens for artery veins and capillaries and not in arteries. Okay? So see those circled ones? Those are ones that already traveled into the tissue, right? Where the site of damage probably is for that mouse. Okay. So then they've clamped the blood vessel, and you can see, look, how dense the red blood cells are. But they don't interact, right? Their job is to carry oxygen, right? So then when they unclamp it, you can see they go flying by. They're not going to interact. Just the white blood cells have the ability to interact with the blood vessel walls, right? And actually go out. So anyone want to gander a guess as to why? There's two main reasons why this only happens in veins and capillaries and does not happen in arteries. I'll have to figure out how to get that to play later. I'm going to close that out. So, yeah, I always do that and then attendance pops up. Okay. What do you think? Why do you think it only happens in veins and capillaries and not arteries? Yeah, we always learn in A&P, A for away from the heart. What is your heart? It's a pump. It's a muscular pump, right? And arteries are the first thing that comes off that pump. So when you think about the pressure, right, and the speed, as you could see even in that video, of those cells, it's too much pressure, it's too fast. That's problem number one. Problem number two is blood vessels, especially arteries, have an additional layer that you don't see in veins and capillaries that actually can change the diameter, right? What is that extra layer? And it's involuntary type of tissue. Muscle, smooth muscle layer. So the cells would have to travel through that layer where you have less layers. Capillaries are just literally, you know, the endothelial layer, one cell layer thick, right? A lot of the veins at that point, right, in those areas deep in your tissues, they're only having to squeeze through the cells that are lining the vessel, the endothelial cells. That's it, right? So it's much easier to actually physically get out, and the pressure is less, right? So it's much easier, right? You're not being pushed along so fast, and you can get out into the tissues, okay? So it's all about, you know, the physiology of it, right? As well as the anatomy of it, of why it works that way. So who is paying attention? This one didn't show it, but you can see it in this picture. So this is who knows what. That's a really mean looking splinter. So number one, we have what happening to this poor tissue by the splinter. We've got tissue damage, right? So those cells are screaming, ow, literally, but in a physical way, right? So they're releasing inflammatory mediators, cytokines, saying, you know, we've been damaged. Plus, what else got in with this splinter? What do you think these things are representing? Bacteria, right? Potentially, right? So we've got invasion. We've got a twofold problem here. We've got tissue that was damaged, and we got invading microbes. Both of these are going to send off the alarm, right? Those cells, right, in resident white blood cells, these macrophages, have a way of detecting that we're going to talk about, and they're going to release signals. But where are the white blood cells? Where are they? What is this representing in this picture? They're in the blood vessel, specifically veins and capillaries, right? So how do they get to the area? What's the superhighway? It's as simple as, y'all, the blood vessels. So we actually, those mediators increase blood flow to that area. So because you have increased blood flow to that area, it becomes what? What do you see? Red, because the blood is red, right? It's also, how does it feel if you touch it? Warm. Your blood is warm. Your blood helps disperse your heat, right? When you start working out, especially people who are Caucasian, light-skinned like me, we get red, right? Because you get more blood flow to the skin, which seems kind of funny, right? I'm working my muscles. What the heck does my skin have to do with it? Well, my muscles are generating a whole lot of heat, right? And to disperse that heat, it goes to your skin, right? And that's how you cool off. And I haven't got to go see them, but apparently we have new elephants at the zoo. I'm so excited. But does anybody know what type of elephant we have at the zoo? Asian or African elephants? Asian. How do you know the difference? African have bigger what? Bigger ears. Because they live in Africa. And it's hot in Africa, right? So the big ears give them big surface area to pump the blood through. And you notice a lot of times they're fanning their ears. That's how they're cooling themselves off, right? Where the Asian elephants, not quite a hot environment, they get to have the cute little ears, right? So we have the cute little ear elephants at our zoo. We have the Asian elephants, okay? But you can visualize that, right? So we've got that increased blood flow, right, to get the white blood cells there. But then they're squeezing out of the blood vessels. Do you see that? What is your blood mostly made out of? It's not actually cells, it's what? It's a liquid, isn't it? Water, right? So fluid leaks out. We can't stop it, y'all, right? When you create those little gaps and cells start moving out, right? It's like little holes in the dam. Fluid's going to go too. So that's your next sign, which is swelling. And that swelling pushes up against the pain receptors, and then you have pain, right? So what do we see when we get increased blood flow? We're going to see redness. We're going to feel heat because blood is red and warm, right? The fluid is also going to leak out, right, which is going to give you the swelling and the pain, Now it makes sense, right? You're like, oh, that's what's going on. Okay, so some of these we haven't gotten to yet. But in that fluid is also a group of proteins, a bunch of different proteins that are really important that are going to help protect. One of them is there anyways because it helps transport iron. So what's the name of that protein that transports iron? In our blood, in the liquid phase of our blood. It transports iron, that's a clue. Transferrin, right? We're going to talk about the complement system of proteins next. Antibodies, which are also proteins, and they're a product of our adaptive immune system, so we talk about, unfortunately, those last. Right? But again, do the bonus, right? I'll start talking about how awesome those proteins are and what they can do, right? And how they can help protect us. And then in anatomy and physiology class, like you, if depending on, I guess, who you have as a teacher, you'll go over the clotting factors, right, that are also in your blood. And these guys are really important. These are what help wall off that scene of damage, right? They're almost like crime scene tape. These are proteins that can form a clot. A blood vessel, if a blood vessel is damaged, we get a clot that forms in it, right? Because we want to control the flow of stuff out of that blood vessel. We don't want it just freely, you know, a dam has busted and stuff flying into that area. And again, but within the tissue itself, right, these proteins, when they get into the area, they can help wall it off, right, and keep stuff in that localized area, right? Because especially as far as the bacteria go, we don't want them escaping this area. Right? We want to keep them contained. We don't always succeed, right? But we want to keep them contained. So how do the white blood cells get out of the blood vessel itself? So what happens here? What's the first thing that needs to happen? Right? So they're in this blood vessel, right? How do they know to come out right here into the tissue? Right, so the first thing is a signal is sent to these cells, the endothelial cells lining the blood vessel, right, to get them to produce adhesion molecules, right? So as their name implies, right, these are molecules that the white blood cells can literally adhere to. And then they're literally going to grab on, right, to those adhesion molecules, and you see in that mouse that rolling effect. Until they get to the point where they literally squeeze through, right? That's diapedesis. And again, it only happens in veins and capillaries because of the whole speed problem, right? Pressure, and you need to just have to deal with one layer squeeze through. One layer cells. So we haven't talked about these guys yet, but in this picture it shows them, and if you've taken anatomy and physiology, you would hopefully maybe recognize that these are a group of white blood cells we refer to as neutrophils. And these guys are really important because one of their main jobs is phagocytosis, to literally engulf and eat the bacteria. Macrophages do the same thing. Right? Macro means big, right? They are actually in your blood called monocytes, right? So when you learn about the different types of white blood cells in your blood, you refer to these as monocytes. They go through some differentiation when they go into the tissues, and they're called macrophages. But you also have these scattered throughout your tissues on guard, but there isn't enough of them. So when inflammation happens, neutrophils, which are your major killers, right, the really good specialists at this, they actually don't go into your tissues unless they're called there, right? Because they're pretty powerful killers. We'll talk about them some more. Macrophages are already there, but more will come, right? And they're big eaters, as their name says. And then if we need the adaptive immune system to come online, lymphocytes, which are your specialized cells for your adaptive immune response. So this is when we say B cells and T cells, right? T lymphocytes is their true name. B lymphocytes is their true name. I usually caution students from using the word leukocyte, though, because you tend to confuse it with lymphocyte. Leukocyte is all white blood cells, right? All white blood cells are called leukocytes. Lymphocytes are a subset of white blood cells, right? So I always say white blood cell, but it's important that you know that definition so you don't get confused, right? Leukocyte is all white blood cells. These are different subsets of those white blood cells. So what do they do, right? So there's a macrophage. See how big he is? There's a neutrophil. What are they actually doing to the invaders? They're eating them, right? They're phagocytosing them. They're actually eating them. And then their other job is to eat any dead cells or debris due to that damage and invasion. So what's pus? So sometimes you'll get a cut, right? And you'll get pus. What pus is dead neutrophils. Dead is not good, right? Because if they're dead, are they doing their job? No. They're losing the battle. So in pus is dead neutrophils. So that's a sign of crap, we're losing. Cell debris, of course, from the damage or even from the neutrophils. And why it's, other than it looks gross, why you should say ooh and not touch someone else's pus is it could contain the pathogens, right, that are causing the infection. When you have pus, you have infection. You have an infection that your immune system is losing the battle, right? When you've reached the level of pus, you're going where? To the doctor, yes. You're seeking medical attention, right? So this is a good summary. It's a little bit different pictures from another book, right? So normal blood flow in the tissues, but then when injury occurs, right, we're going to have mediators released, right? So those pro-inflammatory cytokines, right? Chemical signals from the cells, right? The bacteria, you know, they smell in lab, right? They smell bad in lab. Well, they release things too that our immune system will detect, right? So the alarm has been sounded in multiple ways, right? And because of that, neutrophils are going to come to the area. They're going to be recruited to the area. The resident macrophages, but even more recruited macrophages are going to come to help clean up the mess. How do all of them get there? They've got to come through the blood, right? That's our superhighway, right? All the ones that weren't already there are going to get there through the blood. Hence why we see, right, and feel red, heat, swelling, pain. So just in case you didn't know what it looked like, right, there's some pus. That's the picture from your book. So what's the role of these cytokines? So we've already seen definitely enhancing inflammation, right? Other responses we'll have to infection, especially bacterial infection, because of the different cytokines that are released, we'll get fever. Fever is increase of your core body temperature. That's great, right? Because when you're warmer, chemical reactions happen faster. Things happen faster. But we also know we can use heat against microorganisms, can't we? Right? Heat, to a certain extent, will kill them, right? We have a twofold problem, though. Why is it? So sometimes we stop inflammation because it goes on too long, or it happens in areas that we're going to talk about where it creates more damage than it does usefulness. Same thing with fever. If we get too hot, we're going to hurt even ourselves, right? And that's why sometimes you need to control fever. And the bad news is some bacteria release substances that cause a fever response for us. So they are hijacking our system. So obviously the heat's not bothering them, right? Because that would be pretty stupid for them to make us hot and hurt themselves in the process. But fever that doesn't go away, right? That just keeps going up and up, right? Even sometimes with taken fever-reducing drugs like Tylenol, acetaminophen, right? Or ibuprofen, which ibuprofen is an anti-inflammatory drug. Should you take that on a regular basis? One, no, it'll do damage to your kidneys, cleaning that crap out. And two, you should really only take that unless your doctor tells you to, right? Or you have a plan set up with your doctor as to how often and when you take that. Because it is anti-inflammatory. We just learned today, is inflammation important? Do you need it sometimes? Absolutely. Do you always want to be stopping it? No. 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 Sometimes you prolong the problem by taking those types of drugs because you don't understand what you're doing. A lot of the cytokines, right? So these are the chemical messages of the immune system, are abbreviated IL. This stands for interleukin. Leukin refers to white blood cells. Inner means in between, right? So these are all the ones that they use to talk to each other. And guess what? They're numbered, like IL-1 and IL-6. They were numbered in the order in which they were discovered, right? Not necessarily in the order in which they'd be released under certain circumstances. Tuber necrosis factor, right? TNF. As you can imagine, this was discovered, right, when they found that the release of this particular cytokine actually caused necrosis of tumors. But it is involved in other inflammatory, right, and immune system responses. Ones that are real important, you'll see a lot of times released by cells, is IL-8 when it comes to inflammation. But again, IL stands for interleukin. These all stimulate, right, immune system responses. Again, this is communication, right? So the cell says, ouch. How does it say ouch? It releases things like IL-2 or IL-6, right? Okay, so that's great. Inflammation is meant to be what? Local. Right? In one little area, we've got all these white blood cells running there and eating stuff up. When it goes system-wide, is this good? No. Because think about this, y'all. If you think about the plumbing system in your house, or New Orleans, right? The whole water pressure problem. Remember, your blood vessels, right, have to maintain a certain amount of water in them in order to have the right pressure, in order to get the blood going where it needs to go. If you have fluid leaking out because you have inflammation, what's going to happen to blood pressure? It's going to drop. And the strict definition of shock is an extreme drop in blood pressure, right? But the problem is, a lot of times we don't know what's causing that. Why did your blood pressure go down? Are you having widespread inflammation? Are you having widespread blood loss, right? Do you have internal bleeding, right? And it's just... So the first thing they'll actually usually do is actually give you fluids, right? To get your blood volume up, and then they're trying to figure out, okay, where is the problem? Where do we patch it? How do we save you? Okay? And when you're dealing with pathogens, when you go into what's called septic shock, right, or toxic shock, right? These are specific types of shock which you don't ever want to experience. This is when microbes or their products have gotten into your bloodstream. So now, right, they're in the bloodstream, they're traveling throughout the body, and they're causing the body to release inflammatory mediators, and we're getting widespread inflammation. Septic shock typically means that the bacteria, right, are in your blood, right? They've escaped that local area and they're in the blood. they're going all throughout your body. They're causing widespread inflammation, right? Blood pressure is dropping. Important organs like your brain are not getting blood. And unless we can quickly fix this problem, you're going to die. Notice that the death rates for these types of shocks, even with treatment, range between 30 to 50%. Right? This is when I said, you know, one of my colleagues went into septic shock. Another colleague who teaches microbiology like me walked in. His face looked very much scared and asked a million questions. And our friend that was in the hospital bed was like, well, everyone else didn't freak out. Why are you freaking out? And it's like, well, because I know too much, basically. Right? We know too much about what's going on with our friend, and we're very concerned. With good reason, right? Because no matter what doctors do sometimes it's past the point of return, right? Which is why whenever you're not feeling well, right, at least call the nurse, right? Find out if you need to go in, right? Most doctors' offices keep sick call appointments, right? Open appointments every day just for sick calls. They're a little bit cheaper than the emergency room, right, insurance-wise. Toxic shock, as the name implies, toxins have gotten into the bloodstream. They're just as bad as the bacteria, right? Because, again, they're going to ensue an overstimulation of the immune response. So you'll get, you know, IL-1 and tumor necrosis factor alpha. These are very potent inflammatory mediators, and when these go system-wide, it's not good. And it's hard to shut the system down once it starts. So I was watching a new show last night before the show I watched comes on, and they were talking about a cytokine storm that these poor patients were going under. The show's called The Resident. I don't usually watch it. It just happened to be on, and I was still sitting on the couch. And then that's basically what's happening here. So many cytokines have been released. The first patient that got the drug, they couldn't save him. Even though they tried, timing-wise, they didn't get to him fast enough. Okay? So timing's important, right? Because sometimes it gets to past the point of return. And one of my colleagues, they literally had to, because he went septic, they had to take his blood out of his system and give him blood transfusions to get the bacteria out. And then gram-negative bacteria are really scary because when you kill those bacteria, you release endotoxins, toxins from within their outer membrane, right? So those are really tricky infections to deal with, right? And then, you know, inflammation in the brain. Well, the brain is such a beautiful, important organ, right? It's encased in what? It's pretty hard. Bone. Your skull is made out of bone. Is bone flexible? Not when you're an adult, right? Those fissures have fused, right? When you're a baby, it's still flexible. When you're an adult and you're dealing with inflammation there, right? Yeah, it crushes your brain because it can't swell like skin can stretch, right? And you run into problems there. So yeah, sometimes, you know, inflammation, depending on where it's happening and to what degree it's happening, yes, it can be a bad guy, right? But that's something a doctor needs to figure out, not you. Did you say something, Dylan?
That was kind of funny.
Why?
Like, who's going to put a hole in your skull?
Oh, yeah, I know, yeah, hope that never happens to me. Okay, so, but that's why they do things like that, y'all, to relieve, as they say, the pressure, right? Yeah, boreholes. It's not cool. All right, so how do we know, right, that that bad guys have gotten in, right? The tissues, when they're damaged, they're going to scream. But how do we know that the response needs to be even against a bad guy? So remember, we're still talking about innate, right? So there are certain patterns associated, right, at the molecular level that we have receptors for. So hence they're called pattern recognition receptors. Okay? I hate these acronyms. But y'all think about this. How do we figure out it's a bad guy? We've got a receptor for it. Right? These receptors are in and on our cells, and they are the alarm system. They get triggered. Right? And invertebrates have this, because remember, it's not until vertebrates that we get to, adaptive immune. Plants even have this. They don't recognize individual pathogens, right? They recognize other common molecular patterns. So what are those? Right? So these are Toll-like receptors, because the Toll receptors were originally discovered in fruit fly embryos. But these are membrane bound, transmembrane bound, right? They're in our membranes. They bind to specific things. So we know a bunch of them now, right? So here's Toll-like receptors 1 and 2. Am I going to make you memorize what 1 and 2 can bind to? Hell no. Okay, but we do need to know a list of common things, right? That you already know these answers, y'all. Right? You already know these answers. Once I remove these boxes, you're going to go, oh, I know some of this stuff already. Okay? So, what are some molecules that we've learned about that are unique to bacteria that would say, oh, this is a bacteria that got in? So if you're a gram-positive bacteria, you're gram-positive because you have a thick layer of this substance, peptidoglycan. If you're a gram-negative bacteria, your outer membrane, the outermost covering, is made out of, we abbreviated LPS, but it stands for lipopolysaccharides, right? If you're a gram-positive, you've got so much peptidoglycan that you have additional molecules that almost act as rebar. These are your teichoic acids. So let's see what 1 and 2 is. Lipoteichoic acids, right, which are found, as we know, in gram-positive bacteria. It's also found in some of your spirochetes and your mycobacteria. Which mycobacteria, what's unique about them? Do you guys remember? They lack something. They don't have a cell wall, right? But they have these lipotectonic acids, right? So that's a general molecule, right? But it'll bind to this receptor. Okay, that's all well and good. It's binding to a receptor. Remember, this is the alarm system for the house, right? Whatever cell this is. Who determines what happens and why? The command center of the cell. For our cells, that is the nucleus, and more importantly, the DNA. Right? So notice a signal, right, gets sent all the way to the nucleus. And in this case, it says we need inflammation. Make cytokines, release cytokines, right, like IL-8, that says inflammation here. Come here. Right? So guess what 4 is? LPS of gram-negative bacteria. Some phospholipids of some protozoa will bind to this receptor. What's the same response? Inflammation. The last one is flagellin. There's one for peptidoglycan, but unfortunately they didn't have it in this diagram. But flagellin is the protein that makes up the flagella of bacteria. Right? So again, it says inflammation. Okay, that's on the outside of our cells, right? Notice plasma membrane, outside membrane. Notice in here, in some endosomes, are more receptors that send signals and tell it to release interferon. This is a different response, right? Because this is a different type of pathogen. The most common pathogen that must get inside your cells in order to replicate are who? The viruses. So these are protection. Notice double-strand RNA of viruses. Remember, our RNA isn't double-stranded. Single-stranded. Their single-stranded RNA is still different from ours. That'll set off this set of receptors. Bacteria don't do methylation and capping to their DNA. So internal bacteria, right, will send a signal. And DNA viruses, right, also their DNA is different from ours, different enough that this receptor may recognize it. And we're gonna send off a particular type of response. So notice these receptors, right, what they're binding to, there's still going to be a choice, but it's a general choice, right? Inflammation or interferon response. Are we dealing with bacteria or protozoa or things like that, or yeast? Or are we dealing with a viral infection? Right? So this is like the fork in the road. Right? And you can see all the different things that these cytokines, right, what kind of effects they'll have. This is just an example, right? Not memorizing this. Okay, that brings us to the next section, which you guessed it, I'm not stopping. But I will make it a separate video. I have to hit the right button.